like I'm going to need something to sort of settle my stomach. Hold on. Man, this is terrible. Okay. So I think I'm already in the new share. The problem is I can't see. Okay. Let's find where we are. Goodness, I feel so disjointed this morning now. Okay, we're at the bottom of page 348. Okay, so let me go down here. Okay, we just had done, I think this is where we are. Okay. Do y'all have a better recollection than me? We'll go from current slide. Okay, there we are. Again, folks, sorry. I'm really disjointed this morning. It really feeling pretty rotten. Okay. All right. It seems like I've got a phone call coming in. I can't deal with her now. Okay. It's having to do with my friend's death. We had the memorial service Sunday. That got over with, but I still got messing around with her apartment. And we got as much done as we could yesterday, and that's the social worker, so I've got to contact her later today. Okay, sorry about that. Everything is happening at once. All right. Now, there were no questions, or were there any other questions before we get going today? All right. Where we left off last time, we have been talking about these fundamental trigonometric identities. We've hit them time after time after time. The reciprocal identities, sine and cosecant are reciprocals, cosine and secant are reciprocals, and tangent and cotangent are reciprocals. The quotient identities, also sometimes called the ratio identities, tangent is sine over cosine, cotangent is cosine over sine. Your very important Pythagorean identities, sine squared u plus cosine squared u is equal to 1. You can rearrange that in several different ways to write it, or divide everything by cosine squared and you get 1 plus tangent squared is equal to secant squared, or divide everything by sine squared and you get 1 plus cosine tangent squared is equal to cosecant squared. And you can write those in a variety of ways. Your cofunction identities we talked about before. The sine of the complement of an angle is the same as the cosine of that angle, and vice versa. Tangent, cotangent, secant, and cosecant. And your even and odd identities, all of your trig functions, sine, cosecant, tangent, and cotangent are all odd functions. Only the cosine and secant are even functions. Okay, so those are, in the nutshell, your fundamental trigonometric identities. Okay. The Pythagorean identities are sometimes used in radical form, and I think I mentioned that before too. Remember, let's go back here. If you subtract cosine squared from both sides of this, that gives you sine squared is equal to 1 minus cosine squared. Then take a square root of both sides. You get sine is equal to the square root of 1 minus cosine squared. Or vice versa, subtract sine squared from both sides, and cosine would then be the square root of 1 minus sine squared. And you can do the same things with secants and tangents, and cotangents and cosecants. So lots of ways to express those Pythagorean identities. Okay, and this is just illustrating that. The sine or cosine, just flip them, and tangent and secant, you can't just flip them, but they can be written in different ways. Okay, now notice though, when you take a square root of both sides, you introduce a plus or a minus. How do you know which to use? Well, you have to depend on the choice of u. If this u was in the first or second quadrant, you use the positive because sine is positive in first and second quadrant. If u was in the third or fourth quadrant, you have to use the negative. With tangent, if u here is in the first quadrant, you use the positive. If it's in the fourth quadrant, you use the negative. okay? So you just have to go depending on where the u is. That determines which one of these signs, the SIGN sign, plus or minus sign, that you use. Okay. Now, using these fundamental identities, I think they move. One common application of trigonometric identities is to use given values of trigonometric functions to evaluate other trigonometric functions. Here's the first example showing that. So I'm going to show you a couple of ways to do this. Easy way and what they're trying to get you to do. Use the values secant u is equal to minus 3/2. Time out. Does that even make sense? Can secant be negative? Of course it can. If secant is negative, that means cosine is negative. Well, where is cosine negative? Because remember, secant is a reciprocal function of cosine. Cosine is negative in the second and third quadrants. Okay? Now, cosine is always between plus or minus 1. Secant is always outside plus or minus 1. So secant u, this u must be either in the second quadrant or the third quadrant, and that's perfectly good value for a secant. Okay. Now, they also tell you that tangent u, same u, that tangent u is positive. Well, where is tangent positive? First quadrant or third quadrant? Well, secant was negative in second or third. Tangent is positive in first and third. You must be in the third quadrant. So that these two pieces of information tells you u is in the third quadrant. Remember that. So let's use this information to find the values of all 6 trigonometric functions. Now, I know how they want you to do it, and it's perfectly fine, but there's a much easier way. Okay? So we know, yuck, this is so amazing. Sometimes when I have the pen on the screen, it doesn't write. At other times, I don't even touch the screen and it does write. So this is nuts. Okay? We're looking for all 6 trigonometric functions. That would be the sine of u, the cosine of u, the tangent of u, the cotangent of u, the secant of u, and the cosecant of u. Now this is just how I like to write them, because now you got the reciprocal identities across from each other, and you have the big 3 here and the reciprocals over here. So yeah. Now they told you this one. Secant u is minus 3/2. Now, I've sort of given it away here. What's the next easiest trig function to deal with? If you know secant u is negative 3/2, what do you know about one of the others? Hint. The reciprocal identity, right? That would have to be negative 2/3, because cosine and secants are reciprocals of each other. So all you do is flip them. Keep the same sign, because they always go with the same sign. Okay, so there we have that. Now, the other thing you can think about, now this isn't how they're wanting you to do it, but this to me is the easiest way. What is cosine? Cosine is basically, there's several ways you can express it. That is your adjacent, which is your x value, over the hypotenuse, right? Well, the hypotenuse is always positive, so the hypotenuse is 3, okay? The adjacent must be negative 2. Remember, you're back here in the third quadrant, so yeah, negative 2 makes sense then, okay? Well, what is sine? Sine is y over hypotenuse. Well, it's the same hypotenuse, so you know this is a 3. The denominator's got to be a 3. You know you're in the third quadrant. In the third quadrant, sine is negative. Okay? So all you have to do now is figure out what the y value is. Well, that's where the Pythagorean theorem, the Pythagorean identities come into play. And you know this. Okay? sine squared u plus cosine squared u is equal to 1. You already know what cosine is. That's minus 2/3. Square that and you get 4/9. Okay, so now we know that sine squared u is plus 4/9, which is squaring the cosine, is equal to, I'm going to call this 9/9. Isn't that what 1 is? Subtract from both sides and you get sine squared u is equal to, subtract 4/9 from 9/9, and you get 5/9. Okay, so sine u must be plus or minus the square root of 5/3, right? But guess what, team? We already knew, because we're in quadrant 3, this has to be negative, so we don't mess with the plus, mess with the minus, and this is square root of 5/3, negative square root of 5/3. Well, as soon as you know that, you know this one, because it's reciprocal identity. This is minus 3 over the square root of 5. Now, if you don't like having radicals in the denominator, you could write this as minus 3√5/5. You just multiply numerator and denominator by radical 5. Okay? Now, what you have now, you got 4 out of 6. What is the last two? Tangent and cotangent? Well, that's pretty easy. We've already identified that the y is minus √5. The x is minus 2. So tangent is minus positive √5/2. Why? Because tangent is positive in the, oh, here comes somebody, Azora. So she must have had to bump out and come back in, because I'm pretty sure I got her present already. Yep, got her. Okay. So that has to be 5/√2, and then cotangent is just the reciprocal of tangent, which is 2/√5. Now, if you don't like having radicals in the denominator, you can call that as 2√5/5. There you have it. Okay? All 6 trig functions just from 2 pieces of information. What secant is, and that secant automatically told us what cosine is. Okay? Absolutely, because those are reciprocals. But also the fact that tangent is positive, that tells you which quadrant it's in. 3rd quadrant. Okay? So, if you knew that, you knew basically just about everything else you need. And here comes Morgan. Let me get Morgan here. Okay. Okay. And by the way, was Bennett you the one telling me that Jared's still trying to get in? Did I get his name right? Yeah. Okay. All right. Do we have any questions on this one so far? Now, I did it slightly differently from what the book will do. Okay? Admit that. Okay? I think this is a little bit easier way to do it than the way the book does. But we'll see they use the same principles. So what I'm going to do is clear my, okay, I can't get to my keyboard here. Okay, so I think what I have to do is click on the slide. Now I can. Okay, so let's clear my ink out of the way and see what they do. Okay, now they told you secant. immediately you can use a reciprocal identity and get cosine. Cosine is reciprocal of secant, which is minus 2/3. So 1 over a negative 3/2 is minus 2/3. That's the easy one. So easy. Okay? Now, what they do is go straight to the Pythagorean identity and get the sine. Using the Pythagorean identity, you have that sine squared is 1 minus cosine squared. We know what cosine is, negative 2/3, so cosine squared would be a positive 4/9. 9/9 minus 4/9 would be 5/9, so sine must be either plus or minus the square root of 5 over 3. Well, we know because of this up here that you're in the third quadrant. Secant being negative would put us either in second or third quadrant. Tangent being positive would put us either in the first or third quadrant. Therefore, has to be third quadrant. Sine is negative in the third quadrant, so we use the negative root 5 over 3. So that's what they do. 1 minus this, plugging in for cosine, and that gives us 1 minus 4/9, and that gives you 5/9. And here, because the secant is negative, meaning you're in quadrant 2 or 3, tangent's positive, meaning you're either in quadrant 1 or 3, you have to be in quadrant 3. Okay? If you're in quadrant 3, the sine is negative. So you use that to determine which sine. Moreover, because sine is negative when u is in the third quadrant, you choose the negative root and obtain sine of u is equal to minus root 5 over 3. So, perfectly legitimate, good way to do the problem. I just like to think in terms of x, y's, and r's, x, y's, and h, or whatever you want to do it, and it comes out being the same. To me, it's just a little easier to think through that. Okay? So now that we've got sine, we also have cosecant, because that's reciprocal. Okay? So knowing that the values of sine and cosine enables you to find the value of all 6 trigonometric functions. Sine is minus root 5 over 3. Cosecant is minus, oh boy, did they ever miss that, didn't they? This is correct. That is not correct. Okay? This is minus 3 over root 5. So let me make that correction here. This is root 5. Okay, what they put was secant, okay, not cosecant. That's, oh, here comes Kelly. She must have had to bump out and come back in, because I'm pretty sure she was here before. Yep, Kelly was here. So she's back. So they sort of mess that up. This answer's right, though. If you multiply root 5 numerator and denominator, you get minus 3 root 5 over 5. That one's wrong. Okay, that's a root 5 rather than a 2. Okay, so there's sine and cosecant. We already had cosine and secant, and they got this one wrong. Okay, I don't know what's going on with them. Their graphics person really screwed up here. That's what was given, minus 3/2. Okay, so it can't be root 5. Okay, sorry about that. They messed that one up too. Okay, and then the tangent is simply sine over cosine, which, since they have same denominators and same signs, that makes the tangent positive, which of course it is in the third quadrant, root 5 over 2. And they got that right. Good for them. Okay, well, that would make the cotangent the reciprocal of that. And here is, I don't know who Mackenzie Battaglia is. So I'm admitting them to the class, but I have absolutely no idea who that is. Mackenzie Battaglia, you just came in the class. Are you in the right class? Okay, or are you somebody using someone else's key here? Let me see if Mackenzie Battaglia is in here. There you are. Does anyone know who that is? Oh, did she just leave? Or he? Oh, it is Jared. Okay, I was hoping it would be. Okay, so let me get Jared here. Or I'll call you Mackenzie today. No, I'm just kidding. Okay. All right, so you're here. Good, you managed to come in. Was your system just not operating right?
No, it's just my whole. I need a new computer.
Oh, I see. Okay. Well, don't look here. Okay, good deal. Glad you're here. And let me get out of here. Let me make sure I did mark you at the right place. Yes, I did. Okay. We just finished doing, or in the process of finishing, example 1 on page 349. Okay. The whoever did the PowerPoint screwed up secant and cosecant. They got them backwards. But there we had tangent is root 5 over 2, positive because it's in third quadrant, and that would make cotangent to be, if it will advance, it won't. Cotangent then would be 2 over root 5, reciprocal of this, and if you don't like having radicals in the denominator, it's 2 root 5 over 5. All right, any questions? Now, just a couple things to point out to you, okay? Number 1, if you're in the first quadrant, everything's positive. Everything. All 6 trig functions. If you're in any other quadrant, second, third, or fourth, 4 of them are going to be negative, like you see here, minus, 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 and minus, and only 2 of them are going to be positive. But there will always be 2 that are positive, okay? Except in the first quadrant, everything's positive, okay? But in the second, third, and fourth quadrants, 2 of your trig functions are positive, all the rest of them are negative. Just a thing to keep in mind. All right. Any questions on example 1? Okay. After every example, there is a checkpoint. You can please do the checkpoints as soon as you can after class. And if you're having trouble with them, the audio video solution for those checkpoints are at larsonprecalculus.com. And if you still can't figure it out, turn them in as a homework exercise, and I'll try to help you figure out where you went wrong. So let's move on to example 2. Oh, and here it is. Simplifying a trigonometric expression. That's another thing that your fundamental identities help us with. So how do we simplify that expression? Now notice this is not an equation, it's an expression. We're just going to simplify. Well, one of the first things you do, whoops, here comes Azora again. She must be having difficulty, but I've had her come in 3 times now, I think, but she's here. I'm glad she's here. Okay. Okay, it seems to be happening all over the place. Okay. And by the way, let me go on and get this said now too, since we've got most people here. Do y'all know what next Tuesday is? It's election day. Okay. Now, you might say, okay, big deal. No, it is a big deal. It's always a big deal. Please, folks, I hope you're all registered to vote. I hope many of you have already voted, but if you haven't and you are registered, please, please vote next Tuesday. I get sick and tired of voter turnout being something like 45%, and what that means, 23% of the registered voters decide who our leaders are, because all you need is a majority of those who vote. And if only 45% vote, 23% is going to decide who gets it. Not good. That's not a democracy. Okay? So folks, please vote. Now, why do I bring this up? Besides, I want you to vote. My wife pointed out this morning, next week could be a zoo. If y'all are having trouble, and I was having trouble this morning too on the internet, just think about what next Tuesday's going to be like. Everybody in the world is going to be trying to get on the internet, seeing how things are going. Probably. Maybe not, but it's a possibility. So stand by for heavy rolls. It could be pretty tough getting things done. So anyway, main thing, please vote. All right, what we're trying to do is simplify an expression, not an equation, an expression. When you're simplifying an expression, do the simple things. Notice here you got 2 terms here. Each term has a sign in it, so let's factor out a sign. So factor out the sign. And what it leaves you in the first term is cosine squared x. And when you factor out a sine of a minus sign, you get a minus 1. Okay. Now, something should look vaguely familiar here, but not quite right. This looks a lot like a trig identity, the Pythagorean identity, but it's not quite right because that should be 1 minus cosine squared. Okay? Well, that's exactly the opposite of this. So this would be sine x times negative sine squared x, right? Because 1 minus cosine squared is sine squared, and this is exactly the opposite of that, so that would be this. So this gives you minus sine cubed x. There's that simplified. Okay? Did you understand my sleight of hand here? That sine squared is 1 minus cosine squared, so therefore cosine squared minus 1 would be minus sine squared. Okay? Any question on that? Okay. Let me see if I can get by without erasing. Yes, I can. First, factor out the common monomial factor, sine x. Then use the fundamental identity, the Pythagorean identity. Factoring out the sine gives you cosine squared minus 1. That's not quite the Pythagorean identity, but close to it. It's the opposite of it. So that would be, oops, and here comes Courtney. Good deal. We got Courtney here now. Okay, good deal. Shaping up to be a good class today. Way to go, folks. Okay, Courtney, we're on Chapter 5, Analytic Trigonometry, 5.1, Using Fundamental Identities. We're on page 349, Example 2, the bottom part of the page. And we just are wrapping this up, showing you how the book did it. And the first thing you did, factor out the monomial factor, sine x, and that left you a cosine squared x minus 1. That looks a lot like, but not quite, a Pythagorean identity, because the Pythagorean identity would be 1 minus cosine squared. And this is cosine squared minus 1. So that's exactly the opposite of a sine squared. So it's a negative sine squared. So that becomes, I can't get it to advance, that becomes minus sine. They pulled the minus out here with the sine x, and then this made the Pythagorean identity 1 minus cosine squared, and that would be a minus sine x times the sine squared x. Same difference. That gives you minus sine cubed x. I did it the other way. I made this the minus sine squared x, which is fine. It works out the same way. Any questions? Okay. That was Example 2, page 349. There is a checkpoint following that. Please do the checkpoints as soon as you can outside of class. Okay? Let's see if they're going to do example 3. No! They jumped to example 7. So let's us go to the whiteboard and do example 7. Now, I've got to do some maneuvering around here. Okay, so I'm going to move the taskbar as far out of the way as possible, and I'm going to move the whiteboard in the other direction as far as possible to give me maximum white space to work with. Okay, so let's do example 3. I got to get my book in my lap here so I can read it. Now, we factored out a monomial factor in the last example. Now we're going to do some other factoring. And here's 3a. Secant squared theta minus 1. Okay? Now, I look at that and say, almost, why factor? But they're not asking us if they want to, they're telling us to factor. So let's do it, okay? Frankly, I see no point in this, but we'll do it. This is a difference of two perfect squares. So that would factor as secant theta plus 1 times secant theta minus 1. Now that's a minus 1. The pen is dragging. I don't know why. Let me see if I can make that look a little better. Minus 1. Okay, that looks a little better. We factored it. Now why I said why factor? Well, if you go back into your Pythagorean identities, you'll see that secant, here's what I would have done on this problem, but they said factor, so we factored. But if you look at your Pythagorean identity there, you have 1 plus tangent squared theta is equal to secant squared theta. Okay, well, what happens if you subtract 1 from both sides? Then this goes away and you get tangent squared theta is equal to secant squared theta minus 1. So why didn't I just write down tangent squared theta? I don't know. I do not know why they did it this way. But it's fine. I mean, that's an identity. It's perfectly legitimate. Okay? And that's all they wanted you to do on that one. Now the B part is a little more interesting. Okay? I think anyway. It's 4 times tangent squared theta plus tangent theta minus 3. Now you might look at that and say, wait a minute, how can you factor that? Well, here's a clue, okay? Let's just imagine that function tangent theta is not really a function, it's something else, like a variable, maybe u. So that would be, okay, now this is a little esoteric, but hang with me here. Let's let let u equal tangent theta. Okay? What would we have then? This would be 4 u squared, because tangent is u, plus u, because tangent theta is u, minus 3. And can you factor that? I think so. Let's see if we can. Okay? All we're doing is factoring. Well, what's one possible factorization of 4u squared? Well, you could have a 2u times a 2u, or you could have 4u times a u. I think I want to go with the 4u times a u. 4u times u. Okay? Now, the sign of the last term is negative, so let's make this your minus and this your plus. Let's see if this works. Okay? Then let's put the 3 here and the 1 there, because this is just unfoiling. Okay? Let's see if we did it right. 4u times u is 4u squared. Got it? That's the first. The outer would be plus 4u minus 3u. That would be a plus u, and then a minus 3. That works. Okay? Well, what was u? Tangent theta. That would be 4 tangent theta minus 3 times tangent theta plus 1. Now, I'm sorry my pen is so rotten right here. Okay? Now, did you have to go to the u? No, you could have just treated the theta, tangent theta, as if that was a function. u, or x, or whatever you wanted it to be, and just treat it like that. There you factored. Okay, does that make sense? Another legitimate thing you can do. Now, did we use any trig identities there? No, not really, but it's still true. Okay, in fact, in either one of these we didn't use a trig identity. I did for this one down here, but they didn't do it. They just factored it. Okay, and guess what? Right after that there's a checkpoint. Please do your checkpoints. Okay, they also skip example 4, so I think I'm going to clear my screen first, because this is going to take a little bit more. I don't want to do too crowded. Does anyone need this left up here a little bit longer? No? Okay, let's clear the screen. Example 4. Factor this. Cosecant squared x minus cotangent, that's supposed to be a c there, that's a pretty ugly c, cotangent x minus 3. Wait a minute, folks. You know, the last one, everything was in terms of tangents, okay? And that was fine. But now we have things in terms of cosecants and in cotangents. That's not very fine, because you just can't do a substitution there. However, here's a hint, folks. Anytime you see a trig function squared, think Pythagorean identity. Now, what Pythagorean identity deals with a cosecant squared? Okay, you should know these, but if you don't know them yet, get to know them. Okay, and here's what it is. 1 plus cotangent squared, which is sort of a good thing, x is equal to cosecant squared x. Now, if you don't know that for sure, flip back a page and look at it. That's your third Pythagorean identity. 1 plus cotangent squared u, they use u, I'm using x, is equal to cosecant squared x. Okay? Now, let's take this and plug it in here for cosecant squared, and then you'll have an expression strictly in terms of cotangents rather than a mix. So this will be 1 plus cotangent squared x minus cotangent x minus 3. Okay, combine like terms, and that gives you cotangent squared x minus cotangent x, and then you have a 1 minus 3 is a negative 2. Okay, now if you wanted to go back and do your, say, a u substitution or something like that, you could. But I think it's just as easy just to treat this as a function. Okay, that would be cotangent x times, you're unfoiling, cotangent x. Okay, now you know the only possible factorization of cotangent squared is cotangent times cotangent. Done. You look at your sign of your last term, negative, that means one of these has to be plus and one of them has to be negative. So now we want 2, any possible factorization of 2. That's got to be 2 and 1. Now which one wins? The minus one. So put the 2 here and the 1 here. Now let's check it and see if it works. Foiling, cotangent times cotangent is cotangent squared. Outer would be minus 2 cotangent x plus cotangent x. That would be a minus 1 cotangent x, and then the last would be minus 2. Yep, you've done it. You have now factored a trigonometric expression. No, well, yeah, you did use a trig identity here to get this all in terms of cotangent, and that was a good move to make. All right, any questions on that one? Okay, the next one is example 5. Now this may take a little more room too, so does anyone need that one left up there a little bit longer? Anybody? Okay, so I'm going to clear the drawing here, and example 5. And by the way, this one's also, you can go to larsonprecalculus.com for an interactive version of this type of an example. And here's what we've got here. Sine t plus cotangent t times cosine t is equal to, now this is an equation. You're simplifying, they say a trigonometric expression, but you're actually, well, we'll leave it like that. They say this is equal to, well, wait, they're doing half the work for you, okay? Let's not do that, okay? Here's your expression. Now, how are we going to deal with that, okay? Well, earlier we had an expression all in terms of, say, tangent. Another one we had cotangents and cosecant, so we got them all in terms of cotangent. This one, we got 3 different trig functions, sine, cotangent, and cosine, and there's no Pythagorean identity you can use. What are we going to do? Well, here's my suggestion. Get everything in terms of sine and cosine, okay? If possible, do that. So this first one, it's already in terms of sine, so leave it alone. That's sine of t plus, now what is cotangent in terms of sine and cosine? That's cosine t, this is where we're using our identities, over sine t. Okay? And then you multiply that by cosine t. Okay? So that's done. Well, here you have a fractional form with a sign in the denominator. Here you don't have one. So let's get a sign in the denominator so we can combine these. Okay? So we're going to multiply this one by sine t in the denominator. Okay? But if you do that, you also have to multiply by sine t in the numerator. So what does this yield? This gives you sine squared t over sine t plus cosine squared t over sine t okay, because cosine times cosine is 1. Okay, since you got least common denominator, let's combine them over the denominator of sine t. Add the numerators, sine squared t plus cosine squared t. And can anyone tell me what sine squared t plus cosine squared t is? Please say yes. Your fundamental Pythagorean identity. Sine squared t plus cosine squared t is always 1. So this is 1 over sine t. Oh boy, that really got simpler, didn't it? And we can actually make it even simpler because this is reciprocal of cosecant t. There, we've simplified it really down to a single trig function. Started out being 3 trig functions, none of which were the same, okay, and we got it down to a single trig function all by itself, cosecant t. And that was example 5. If you look in the book, you'll see that's what they did. And that's followed by a checkpoint. Always do your checkpoints as soon as you can outside of class. Okay? So let's move on to any questions on example 5 or 4 or 3 or 2 or 1. Okay, any questions? Okay, example 6, top of page 351. let's clear the slide. Does anyone need this up here a little bit longer? No? So let's clear the drawing and let's do example 6. Now, I'm having trouble reading it, so let me get it in my lap here. Perform the addition and simplify. So here's your addition. Sine of theta over 1 plus cosine theta. Okay, plus cosine theta. Okay, I don't know what the noise is, but if someone's trying to reach me, go on and spit it out, okay? Cosine theta over sine theta. All right, now remember my earlier suggestion, get everything in terms of sines and cosines. They're already everything in terms of sine and cosine. So what do we do with this? Well, you can't add fractional forms unless you have least common denominator, right? So what is the least common denominator between 1 plus cosine theta and sine theta? Well, it's the product of the two. So basically what you have to do here is multiply this by sine theta. If I could get my pen to write. But if you multiply the denominator by sine theta, you also multiply the numerator by sine theta. Okay? Well, you got this one to be fairly complicated. What you have to do here is multiply this by 1 plus cosine theta. 1 plus, get out of there. 1 plus cosine theta. Okay? But if you multiply the denominator by that, you must multiply the numerator. Goodness gracious, this thing is so aggravating. By 1 plus. This thing is so aggravating. 1 plus cosine theta. Okay. Well, we got a little bit of cleaning up. We got least common denominator now, so we're going to hang on to that for a moment. So let's just write that as our denominator here. That would be sine theta times 1 plus cosine theta. Now, by the way, is there any advantage to going and multiplying that through? Not that I can imagine now. Leave it as simple form as you can, factored completely. Okay, so that's your denominator. Your first numerator here is just sine squared. So that's going to be, goodness gracious, this thing is aggravating. Sine squared theta, that's from here, plus, now let's distribute at the same time. That's plus a cosine theta. That's when you multiply cosine by 1, plus cosine times cosine is cosine squared theta. Okay, got it? Now, that's pretty good, except it's not quite in the order I'd like it. Why would I like it in a different order? Because I recognize that sine squared theta plus cosine squared theta is equal to 1. You're a Pythagorean identity. So this would become sine squared theta plus cosine squared, I'll write them together. Sine squared theta plus cosine squared theta times, or plus, cosine theta over sine theta times 1 plus cosine theta. Now, if you think something's shaping up here, I believe you're right. Because what did we say this was? Sine squared theta plus cosine squared theta? 1. So this would be 1 plus cosine theta over sine theta times 1 plus cosine theta. Well, guess what? 1 plus cosine theta over 1 plus cosine theta is simply 1. Okay? So this would again turn out being 1 over sine theta, which happens to be reciprocal identity cosecant theta. Didn't know you'd be running into so many cosecant thetas, did you? Except these are thetas, or are they t? Yeah, these are thetas. The previous one was t. Okay? Any questions on that? You see how that worked? Okay. Carry things as far as you can. Use all the tools in your tool belt. Least common denominators, factor, whatever it is. Try what you can. See if you can get it to simplify. And if you do, see what it simplifies to. So that was example 6. And there is a checkpoint right after that. Please do your checkpoint. Okay. Now, my memory is they did do example 7. So let's go back to our slideshow. And move on to example 7. Now, hold on just a minute, folks. I'm kind of losing it again. Hold on. Okay. Here's example 7. Sorry about the delay. Okay, how are we doing on time? We're fine. Rewriting a trigonometric expression. Boy, this is pretty strange. Rewrite 1 over 1 plus sine theta so that it is not in a fractional form. In other words, you don't have a denominator. Ooh, how are we going to do that? Okay, well, I've got to find my pen. There it is. Okay, so let's write it down. 1 over 1 plus sine x. Okay, now let me give you a hint. You've run into this before, though you may not have recalled it. Okay, whenever you're trying to simplify something that is of the form a plus b, 1 plus sine x, one thing you can try is multiply by its conjugate. Okay, so let's multiply this denominator by its conjugate, 1 minus sine x. But if you multiply the denominator by the conjugate, you must multiply the numerator by that same expression, 1 minus sine x, right? Because this over that is 1. You haven't changed a thing. Except, let's look at what that denominator is. A sum times the difference of the same two quantities would be 1, the difference of their squares. 1 minus sine squared x. Okay, and this is all under 1 minus sine x. Okay, well, hopefully that rings a bell there. This is cosine squared x. So this will be a 1 minus sine x over, that's your numerator, over cosine squared x. Pythagorean identity. Okay. Now, you can rewrite this as 1 over cosine squared x minus sine x over cosine squared x. Right? Well, from your reciprocal identity, this is secant squared x, right? Minus, well, sine x over cosine, let's split this apart, sine x over cosine x times 1 over cosine x. Okay, because sine x over cosine times 1 over cosine. This would be secant squared x minus what, sine over cosine? tangent x times 1 over cosine is secant x. Now, what you might do, you don't have to, but you could factor out a secant x times secant x minus tangent x. That doesn't really help you any, but you could do it. Okay, so either one of these, this form or this form, is not in a fractional form. Done. Now, is that the only answer? Probably not, but let's see what they got. They left it in this form down here. If I can find my pen again, here it is. This form down here, secant squared x minus tangent x secant x. Perfectly fine. Not in fractional form. Is that any simpler? In my mind, no. It's rather complicated, but at least it doesn't have a fraction. It doesn't have a denominator. It's not in fractional form. And if that's what you're looking for, you got it. Okay? Now, let's see if they did it any differently from what we did. Any questions before I erase this? Okay. See what they do first. From the Pythagorean identity, cosine squared is equal to 1 minus sine squared, and that's equal to 1 minus sine squared times 1 plus sine squared. Multiply both the numerator and the denominator by 1 minus sine squared x, 1 minus sine x, will produce a monomial denominator. That's what you're looking for. Okay? But doing it the way they do it, you have to really look into the crystal ball and see what you're trying to get to before you ever get there. Okay? That to me is a bit of a stretch. So what I like to do is think of this as, well, this is a form, 1 plus an entity multiplied by the conjugate. That's usually the safe thing to do. And that's exactly what they did here, but they went through all this rationale for doing it, which if you look at this and say, well, I'll just multiply by the conjugate, see what happens. That's what happens. Okay? It just happened to be, it worked out for you. And it wasn't just happen, okay? Because multiplying by the conjugate does give you a difference of two perfect squares, and that difference of perfect squares just happened to be your trig identity, your Pythagorean identity. So go with it that way, rather than, oh, because you see this is going to happen, we're going to do it this way. I don't really like that approach. If you like it, go for it. It's perfectly fine. So anyway, they did this, multiply numerator and the denominator by the conjugate, 1 minus sine x over 1 minus sine x. And when you do that, you wind up with 1 minus sine x over 1 minus sine squared x, which is cosine squared x, which now gives you a monomial denominator, always a better idea. And then once you have that, you can split that into 1 over. See, if you have a monomial in the denominator, you could put this part over that minus that part over that, which is exactly what they did. This becomes a secant squared. This becomes a tangent x over times 1 over cosine, which is a secant x. So that's what you get, 1 over cosine squared x minus sine x over cosine x times 1 over cosine x. Well, it's just gotten worse, it looks like, but guess what? This is a secant squared x, this is a tangent x, and this is a secant x. You've lost all your denominators. Okay? You only had a 1 plus cosine to begin with. You got it to a monomial. You split that into smaller pieces, and then you got it with no denominators at all. Any questions? All right. That, they say, is the end of the slideshow, example 7. Okay? By the way, there's a checkpoint after example 7. Please do your checkpoints. There's still example 8 and 9 to go. We've only got 3 minutes. Let's see what we can do on example 8. I doubt if we'll finish it, but at least we can get it started. Okay? So let's go to our whiteboard, clear it out of the way. Does anyone need this any longer? Okay. Here's what we got. Use the substitution. Oh boy. I think this is going to take more than 3 minutes. 2 minutes now. So let's hold there and we'll start next time with example 8. Okay. So let me erase my previous mark and put example 8 back into place. Okay. And we'll begin there next time. Homework exercises here beginning on page 353, 5.1. Any of the odds 7 through 11, they're all at Calc Chat. 7's at Calc View. Any of the odds 13 through 17. Actually, if I were you, I would do all 6 of those, 13 through 18. Only the odds have answers in the back, but they're also at calcchat.com. But see if you can match them up the way they mean for you to, and then you can check the answers 13 to 17. Then do either 19 or 21. They're both at Calc Chat. 19's at Calc View. Any of the odds 23 to 31, they're all at Calc Chat. 25's at Calc View. Any of the odds 33 to 39, they're all at Calc Chat. 35's at Calc View. 41's at Calc Chat. This is on page 353, starting there anyway. Okay, 41's at Calc Chat. Any of the odds 43 to 47, they're all at Calc Chat. 43's at Calc View. And I think you can do 49. It should be at Calc Chat. I believe you can do 51. It should be at Calc Chat. Hold off there though, and we'll pick up the rest of those next time. All right, good deal. Any questions? Okay, sorry we got a late start today. Completely outside of my control. Sorry about that. Next time we'll pick up with 5.1, finish those last 2 examples, and then move on to 5.2. So, any questions? All right, well then I'm going to stop sharing. I'm sick and tired of sharing. And if there's no objection, I'm going to end the meeting for all of us. So any questions before I end it? Okay, take care folks. We'll see you on Thursday, and hopefully you're voting next Tuesday. Try to do it either before or after class, but vote. No matter what, vote. Thank you. Bye-bye.